All right, everyone. Let's just get started really quickly here. Wait, where's on? Can you hear me, everyone? All right. There we go. So, hello, everyone. I am James Gao. I am a fifth-year graduate student in the Vision Science program here, and I'm working mostly on visual neuroscience. So, since you guys have already seen quite a lot of scientific computing in Python already, I figured I'd give you kind of an end-to-end overview of one of a common processing pipeline in neuroscience. So to start that off, I'm going to give you kind of a little of an overview of what the data set I provided to you guys is and how we operate on it. And then we'll go ahead and go straight into the IPython notebook and just run the whole data processing stream on it all at once. So just to kind of demonstrate to you all the visualization visualization possibilities in Python, and also introduce you guys to at least the names of some of these packages that are kind of new and upcoming and also very important in Python now. So just to start things off, in neuroscience, an experiment can actually be extremely simple. We can show this brain right here, a picture of a tin of Spam, and we can record some kind of brain activity coming out of that brain in some methodology, one of which I'll describe to you later. And the ultimate question in neuroscience, the question that we really want to answer here, is basically, what did that brain do, right? If we knew what the brain did, then we can feed it arbitrary pictures of cats, pictures of people, and it'll do the same thing as a brain, and now we can declare victory. We can say that if we can make this thing, it'll be, in effect, the same as a brain. So how do we do something like that? Well, we can take a cue from the control process people and try to do something called system identification. So in this case, we're basically treating the brain as a big black box. And if we can somehow make the black box take the same picture of the tin of Spam and give the exact same signal out of it, if we can maximize this correlation, then we can declare victory. Our black box is now a black box brain that is basically doing what a human brain is actually doing. And one of the ways that we can do that is through just linearized regression. So I realize that most of you probably aren't neuroscientists here, but a lot of the techniques I'm going to use here are actually common in a lot of different fields, and my roommates are astronomers, and we are able to discuss more about the techniques than other people in the Vision Science program when I'm talking, so trying to kind of gives you an idea of how pervasive this kind of math is now. So the method of the type of data that I have provided you in the neuron.hf5 file is called electrophysiology data. That data set is actually simulated. And electrophysiology data is basically collected by sticking a small metal probe into some brain tissue and then looking at the electrical signals coming out of the brain. So based on previous publications, we know that basically you can regard a single cell of the brain, the neuron here, as operating as kind of a linear filter on the stimulus. So if you show this neuron, if you input some sort of like a white noise pattern, for example, and it matches this filter that it sees, it'll basically fire off a spike, an electrical spike, basically a large change in electrical potential. So this is kind of an idealized version of a neuron. Real neurons don't really look like that. What I provided you guys in the raw signal looks more like this blue trace right here. So you can see that the blue trace here, you get lots of nice noisy electrical noise. You also get this kind of weird oscillatory component, and you also get these nice clean spikes here. And it basically becomes a problem here now. You have this modeling problem that you want to address. You want to figure out what is the linear filter, but you have this data. What do you need to do with it? So obviously we need to pre-process the data, and this kind of pre-processing is very common through many different fields. In this case, we actually need to run two different frequency filters. A low frequency filter, in this case, gives us a kind of signal known as LFP, which is just low-frequency oscillatory components in the brain. And if we're concerned about the spikes, these things that the neuron fires for, that when it sees a filter that it likes, if we're concerned about those spikes, then the LFP is basically noise. We need to get rid of it. So once we get rid of this LFP, we're left with these nice clean spikes. And the thing is, since you just stuck an electrode into the brain, we don't really know which cells is actually hearing stuff from. So in this one channel, you're actually going to get a linear combination of many different cells. So we're also going to have to run a classification, in effect, to figure out which cell fired which spike. So once we have this pre-processing step done, we basically get a raster plot of the times at which each cell fired. And after we get that raster plot, we can basically just do our straight-up linear regression now and take our stimulus and run linear regression on the raster plot and basically get our filter back that we expect the neuron to be actually responsive for. So let's just switch straight over to the IPython notebook. We have the scicomp2 file IPy notebook that I sent out. So let's go ahead and just open it. I'll kind of describe this to you guys line by line, even though it's already typed in. So last year it was kind of a fiasco when I had to type everything in and no one could follow along. So the first line is just a whole bunch of imports. I'm sure you guys have already seen the NumPy import already. And the second line is a PyTables import. I think you guys touched up on it briefly in the scientific computing first session. And this tables is a kind of a data format that is supported in both MATLAB and Python and a whole bunch of other software packages. It's kind of it's one of the better ways of saving large matrix form data sets, and it actually lets you slice into it arbitrarily, kind of like a memory mapped array. So it's efficient for very large data sets. We have scipy.signal, which gives us access to a lot of the signal processing routines, so doing the filtering in effect. We have this new package called scikit-learn, sklearn. That's actually a very good package. I suggest you guys go on their website. If you just search scikit-learn on Google, you'll get their website. It's a very comprehensive machine learning package in Python, and people are actively developing for it and introducing a lot of cool new machine learning algorithms. So in here, I'm actually just going to import the submodules, the decomposition modules, which actually give you various matrix factorizations like principal components analysis, PCA, or independence components analysis, ICA, fast ICA. I'm also importing the mixture submodule, which is basically the Gaussian mixture models. Various kinds of Gaussian mixture models. Scikit-learn actually gives you everything from just plain Gaussian mixture models, which are basically probabilistic k-means, all the way up to dirichlet process Gaussian mixture models, which actually try to do model selection for you on the fly using a dirichlet process. And finally, I'm also importing the linear model, which actually gives you many different varieties of regularized linear regression if you want to do the final modeling step in this case. And this last package I'm importing is a really cool package called Myavi, and that's for doing 3D data visualization. And this is much faster than MATLAB's implementation, which is mostly just 2D plotting. Myavi actually gives you access to the full capabilities of your graphics card, and I've actually personally programmed some very advanced brain visualization toolkits using Myavi. And I'll demonstrate how to use this later on. So let's go ahead and just shift enter this and import everything. Okay, so it's imported. So first things first, let's open up our neurons file. So if you guys haven't gotten this file already, I suggest you go ahead and go back to the Python Bootcamp info website and download this file and just kind of play along here. Let's open this file and then just print it out, and we can directly plot one of these raw data traces. So let's shift enter here. You can see that this file right here actually gives you a little bit of metadata. And the metadata tells you that it was modified some date, and it also tells you that there's actually two different data sets in this file. So the HDF5 file format is a hierarchical data file, hence the name. So the HDF5 file actually lets you store multiple data sets in a nested group, in any nested format that you like. So it's a very flexible format. And again, it lets you do kind of arbitrary slicing into it so you don't destroy your RAM if you have a very, very large data set or something. So I'm actually providing you both the raw data as well as the stimulus data that I use that basically create this raw data. And if we look at the plot, we can see that this plot looks kind of like that trace that I showed you earlier. You get this high frequency spiking activity, and you also get this low frequency oscillatory component, as well as the electrical noise that you expect to find when you just stick an electrode somewhere. So we have this raw signal. What do we need to do with it? So like I mentioned before, the first thing we need to do is basically filter it. So this part is very similar to MATLAB. The first line here just creates a third order Butterworth filter that cuts off at 0.1 times Nyquist. And that gives you the filter coefficient. So this is basically just doing filter design. And I'm just going to use a standard forward-backward filter that doesn't introduce phase shifts on this raw data. And I'm using this colon here to basically select all of the data because I want to pull all the data off the disk and filter it and store it into this LFP. And here I'm just plotting the first 1,000 time points. If we plot it, and we can see that these two plots are actually time locked, and you can see that it looks like a low frequency response of this upper plot. So we know that now in this variable LFP we have this low frequency signal. If we want just a high pass version of that signal, we can just take the original raw signal and subtract off the low frequency component. And if we plot the first 1,000 data points, we see we have this nice high frequency high pass filtered version of the raw signal. And you can still see these nice sharp spikes in here. So once we have these spikes, remember we now have to figure out which cell created those spikes. So now we're switching over to our classification problem. And the typical way that we do this is basically through a process called cell sorting, where you look at the waveform, how each little section of this data look, and compare it to different ones and try to create classes to figure out what each cell looks like in effect. Well, actually, the first step we need to do is basically figure out when these spikes occur. So what I'm doing here is basically just thresholding the data. So every time it exceeds 5 here, so if we look at 5 right here, it looks like every time it exceeds 5, it looks like a spike. So let's just go ahead and filter that, show the binary form of that signal, and you get these nice spikes. And now we have to slice out the chunks of data where those occur. So first things first, we can just basically figure out when those spikes occur by using this differential to make sure we don't get the start and the stop. And that gives us the times at which these spikes occur. We have at time point 13, we have a spike, which is up here. At time point 43, we have another spike. At time point 103, we have another spike right there. So this is kind of what you'd expect from the binary, basically just finding the times at which the binary kind of blips up. And now we're doing a little clever list comprehension here, which basically takes every single one of these times that we selected earlier and slices out a 30 sample chunk of the signal from that. So if we go ahead and just run this line here, what we've done now is the spikes.shape shows you what kind of the shape of the data. What we have is basically 1,100 different spikes and 30 samples for each spike. And we plot the first 100 spikes, they look like this. And you can actually see already that there's basically kind of 3 different shapes for these cell spikes. So we expect to find probably about 3 different neurons in this one raw signal.
Is there much more data than what we saw up earlier there?
Yes, this is only the first 1,000 time points.
Oh, okay.
Yeah. So if I plotted them all, it would just be a dense mishmash of blue. You wouldn't see anything. So if you notice, I sliced just the first 1,000 right here. So in this data set, this example data set, I provided about 1,200 spikes just to give you enough data to do the system identification later on. So now we have this massive data set that has 1,100 samples and 30 dimensions in effect. What can we do with it? We'll probably have to do some sort of dimensionality reduction, because if you want to do good good classification, you can't have too many dimensions, otherwise it becomes a very hard problem. So let's just use principal components analysis to reduce the dimensionality of the data. So this is, again, from scikit-learn. You can use decomposition and then get the PCA object, and you're defining that you want only the first 3 dimensions from the PCA. And you can fit the data and then transform it and get the projections of that data. So done. It's really, really fast to do that, because it's just an eigenvalue decomposition. It's really fast. But now here's a little cool bit. We want to see all the projections in 3D. So since we defined 3 dimensions, we can just look at it in MyObby. And sorry for this little bug here. I set an option somewhere, and I don't remember where, but this fixes it. You guys should already see this structure. And if you drag, you can see that it's actually nice and fast and smooth. And you can actually see that there are probably approximately 3 different clusters in here, right? We have a cluster that seems to be right here. Another cluster that's kind of elongated right there. And we have a separate cluster that might be right over here. And this might be another neuron, but it's hard to tell. And MyObby actually has a lot of really cool features. I suggest you try to explore it. Points 3D is just the simplest, let's plot the points out. But I mean, the amount of features in here are immense, so here's kind of a stupid one, but if you have red-blue anaglyph glasses, you can turn that on and actually see it in 3D. It's much more impressive if you actually had more advanced data than just this cluster of points. So a lot of things are possible with MyObby. I definitely recommend you give that a try. Yeah.
I should say that if you install the 64-bit version for Mac of the from Enthought, MyObby won't work.
Oh, really?
So if you really need MyObby, go back to 32.
Oh, that's annoying. Go figure. In any case, MyObby has a lot of cool toolkits because they. Oh, yes.
What's the difference between MyObby and MyObby 2 and
So MyObby is basically just an advanced wrapper around the visualization toolkit VTK. And VTK is kind of this old C++-based toolkit for accessing a lot of scientific visualization tools, but it's written in C, so it's kind of a pain in the ass to use. TVTK was basically Enthought's attempt to wrap VTK using their library called Trace, which actually gives you a nice GUI interface for changing basically twiddling all the knobs all at once. And then MyObby then took these TVTK objects and created an even simpler wrapper around that to give you access to these very advanced visualization functions using a very simple interface. So the other cool thing about MyObby is you have this little pipeline window here. If you click on that, it actually gives you a lot of things that you can do with it, all like on the fly. So for example, you can change how, sorry, this computer is a little slow. You can change how all the glyphs look, because you can. Where is it? Glyph source, there we go. Sphere source, so let's change them to axes if you want those instead. And see, it's all dynamic and it gives you a lot of functionality all at once. So if you need more information about that, I'd recommend checking out MyObby 2. So MyObby 1 was the original version that I don't think Enthought was the one who made that. But MyObby 2 is the Enthought project that is much more better developed, so give that a try. Any other questions?
Do you import MyObby 2 or MyObby?
Just MyObby.
Oh, okay.
Yeah, from MyObby import mlab. That was the command. So again, if you look at the MyObby website, they'll give you a whole list of different plotting functions that give you, a lot of different things. So you can plot 4D charts if you wanted to, take 3D slices, for example. there's a lot of ways of accessing MyAvi functions that are very, very powerful. Okay. So we see that there's approximately about 3 clusters that we want to pick out. So let's just run a very, very simple classification algorithm. Let's use Gaussian mixture models. So Gaussian mixture models is, in effect, probabilistic k-means. So if anyone's familiar with k-means, basically you have a cluster of points and you randomly drop your cluster centroids in your space, and then you basically assign the closest points to them and then shift the centroid. In Gaussian mixture models, instead of assigning points to a single cluster, you basically give it a probability using a Gaussian distribution around that cluster. And then you have a probability belonging to each cluster, and you kind of shift the Gaussians around until they converge. So in this case, I'm creating from the mixture submodule, I'm getting the Gaussian mixture model object. I'm saying that I want three mixtures in the end. I'm going to fit that model to the projections. And that gives me this GMM object right here. And then using this GMM, I can actually just directly predict the original data, and it'll give me basically the labels assigned to each spike. So if we print the first 10 labels, you can see that, look, it thinks that the first 4 spikes belong to class 0, and the next spike belongs to class 1. So this is just a really quick and simple way of doing classification effect, and that allows us to basically create the raster plot, which is what the next step does. So in this box here, I'm actually starting with basically a 0 matrix, and has the length of, basically it's the time by the number of unique labels. So basically that's saying how many cells I have. And then for each one of these unique labels, I'm basically selecting each time it is found in the times and setting that as 1 where they occur and 0s where they don't. So if we just plot that data set, we should get 3 different lines. And again, since I'm only plotting the first 30 time points here, we can see that we have a spike here, spike here, spike here, and this is a different cell, so it's a different color, so it's a different line. So now we have that raster plot that we needed to start our modeling procedure. So we can actually go on to the regression step and try to figure out our linear model, basically figure out what each cell cares about. So here I'm in this next box. The first line is, again, I'm just pulling down the stimulus, all the stimulus time points, basically the stimulus that the neuron saw at each time. And then I'm creating this new ridge object, which is basically just taking off regularized linear regression. I'm giving a regularization parameter of 10. Typically, you would actually use cross-validation to figure out the correct, the best ridge parameter here. But scikit-learn actually gives you many functions for doing everything from generalized cross-validation all the way through just plain old grid search. And they give you a lot of functions for doing this. And it's really powerful, so you can check it out. But let's just pick 10 for now because it's a convenient number and it's fast to run. So here we just fit this linear model to the stimulus and that raster plot. And bam, it's done. We have our model already. We have the coefficients of the model get stored into this coef model. So basically, that's what your weight matrix is. And since we had 3 response channels, in effect, we have 3 model weights, and we can just go ahead and look at them. If we just plot them, you can actually see that this cell cares about this kind of a biphasic spike. And this next cell cares about, this one's a little noisier, it's just a single spike in the middle. And this last cell is, again, a different, slightly noisier biphasic spike. So basically, this is just a very simple example. It's going through all the steps from this raw data stream, filtering it, pre-processing it, doing classification on it, and finally doing full-blown modeling on it. And notice how quickly it went by. So Again, the packages that I used here are mostly scikit-learn. SciPy has a lot of the functions already, which is installed on most computers. And Mojave also gives you all the 3D visualization toolkits. So if there's any questions, that's all I have. Yeah?
So I don't know a lot of algorithms you discussed, so just curious, what kind of information can you
Sure.
get from this?
So basically, this trace here is basically if you had, if the neuron had 100 inputs into it, and the 100 inputs looked like this, the neuron would spike. The neuron spikes whenever the inputs look like this, in effect. So if you imagine this to be an image, if you just unraveled it and put it all into a line, if the image looked like kind of like this little wavy shape, the neuron spikes whenever it sees a wavy spike that looks like this. That's just, this is just a very short example data set, so I didn't really try to make it too realistic. But if you actually try to do this kind of regression with actual neural data, you'll see, especially with visual neurons, you'll see small little kind of like Gabor functions. Yeah?
Curious, when you're actually doing analysis, what is your workflow? Sort of thing? Do you work in the notebook or do you work in
So
the
this is a fairly simple example from my personal workflow. Usually I'm actually developing algorithms, not just using the existing ones. So in that case, I actually do need to use the original, the console version of IPython because I need the debugging mode, which isn't supported yet. Yeah, but if I needed to run an analysis that I had code for, like this one, for example, then yeah, by all means, I would probably do it in here because it's just so much easier to just plot it out. It's really, really fast to kind of interact with it and see what happens. So this is definitely the preferred way of doing things, if possible. Yeah?
After you disambiguated the different neurons, when you go back to the random dot patterns, what kind of receptive field structures do you find?
In this case, I kind of simulated a very simple, the simple cell receptive field architecture. So if you basically just took if you just weighted the firing rate of the neuron by if you just weighted each one of the random dot patterns by the firing rate of the neuron at that time, and just average those together, you'll actually see the neural receptive fields. And most of the time in early visual cortex, you'll actually see small Gabor functions, which are basically just sine wave gratings with a small Gaussian window over it. And that's a typical form for early visual cortex. You'll also get cells that are phase invariant, so they don't care about light or dark versus dark or light. That's basically, and also a lot of movement sensitive cells. So if you actually average a small time course around the times at which those occur, you'll actually see kind of this little grading shifting around in the receptive field. So depending on which cells you actually get a pretty big variety. And that's the early visual cortex cells we know the most about. Those work pretty well. And beyond that, we have really crappy models for. So that's an area of active research. In fact, I happen to know that two of the stats people from my lab are working on just that problem right now. Okay, any other questions? Okay, that's it. Thank you. Treating the brain as a big black box. And if we can somehow make the black box take the same picture of the tin of Spam and give the exact same signal out of it, if we can maximize this correlation, then we can declare victory. Our black box is now a black box brain that is basically doing what a human brain is actually doing. And one of the ways that we can do that is through just linearized regression. So I realize that most of you probably aren't neuroscientists here, but a lot of the techniques that I'm going to use here are actually common in a lot of different fields, and my roommates are astronomers, and we are able to discuss more about the techniques than other people in the vision science program when I'm talking. So I'll give you kind of a little of an overview of what the data set I provided to you guys is and how we operate on it. And then we'll go ahead and go straight into the IPython notebook and just run the whole data processing stream on it all at once. So just to kind of demonstrate to you all the visualization visualization possibilities in Python, and also introduce you guys to at least the names of some of these packages that are kind of new and upcoming and also very important in Python now. So just to start things off, in neuroscience, an experiment can actually be extremely simple. We can show this brain right here, a picture of a... All right, everyone, let's just get started really quickly here. Wait, where's... On. Can you hear me, everyone? All right, there we go. So hello, everyone. I am James Gao. I am a fifth-year graduate student in the Vision Science program here, and I'm working mostly on visual neuroscience. So since you guys have already seen quite a lot of scientific computing in Python already, I figured I'd give you kind of an end-to-end overview of one of a common processing pipeline in neuroscience. So to start that off, I'm going to spam, and we can record some kind of brain activity coming out of that brain in some methodology, one of which I'll describe to you later. And the ultimate question in neuroscience, the question that we really want to answer here, is basically, what did that brain do, right? If we knew what the brain did, then we can feed it arbitrary pictures of cats, pictures of people, and it'll do the same thing as a brain, and now we can declare victory. We can say that if we can make this thing, it'll be, in effect, the same as a brain. So how do we do something like that? Well, we can take a cue from the control process people and try to do something called system identification. So in this case, we're basically trying to kind of gives you an idea of how pervasive this kind of math is now. So the method of the type of data that I have provided you in the neuron.hf5 file is called electrophysiology data. That data set is actually simulated. And electrophysiology data is basically collected by sticking a small metal probe into some brain tissue and then looking at the electrical signals coming out of the brain. So based on previous publications, we know that basically you can regard a single cell of the brain, the neuron here, as operating as kind of a linear filter on the stimulus. So if you show